Hello, everyone, and thank you for coming to Virtual Grads 2020 and checking out my poster. So let's get started. My project combines computational modeling and laboratory experiments to try and predict pollutant reactivity based on its structure. Specifically, we're interested in a pollutant known as polyfluoroalkyl substances, or PFAS for short. In broad terms, PFAS are compounds that contain carbon-fluorine bonds. These compounds are ubiquitous in manufacturing due to the fact that they have many unique properties. For one, the CF bond is one of the strongest bonds known in organic chemistry, which makes PFAS extremely unreactive and hard to degrade. This is of concern because they're often released into the environment and contaminate everything from food to water to soil. So it's no surprise that 99% of people test positive for PFAS in their bloodstream around the world. As mentioned earlier, these compounds are extremely unreactive. This poses an obvious problem in that once they're introduced into our bodies and the environment, there's no natural way to get rid of them since they're man-made. If we're able to predict how reactive these pollutants are, then we can rationally design new PFAS that retain their desirable properties while making them less toxic and more amenable to degradation so they don't stick around for so long. We essentially want to build some kind of mathematical model that takes chemical structure as its inputs and outputs reactivity. This will allow us to design PFAS that are more reactive and thus more amenable to degradation. To do this, we'll first try and establish trends in reactivity of different PFAS using experimental techniques such as laser flash photolysis. And this technique allows us to examine the kinetics of reactions. The scheme is outlined up here. So basically, we can degrade or defluorinate these compounds using this method and determine rate constants using plots such as these from their slopes. Some of the trends that we've actually determined thus far are outlined right here. And once we know how fast these compounds are reacting compared to each other through these trends, like this one right here, we can use DFT to calculate properties of these molecules and use statistical analysis to further examine which properties are best at dictating its activity. So just a few properties we're interested in calculating are bond dissociation energy, energy of the lowest unoccupied molecular orbital, reduction potential, dipole moment, and things like that. So our resulting mathematical model will look something like this guy down here, which is just some linear combination of these molecular properties, and again will allow us to design PFAS that are still useful in manufacturing, but also more amenable to degradation. And this is just some dummy equation that I put in for different properties. Basically, you'll just put in calculated properties and the model should calculate activity or how reactive it is. And using this kind of model, we'll call this rational design. Thanks for checking it out. Bye.